Log on, tune in, find out. Another good idea from Cambridge.
So our last speaker, is that the right slide, Ben? Is that okay? Slide okay? Yeah. Our last speaker is Ben Torsney from the University of Glasgow, whose title seems somewhat different than here. Formulating and fitting copula-based latent variable models for paired comparisons and ranking studies. Ben?
Okay. Well, Glasgow is a place that's a bit further north than here. Actually, I come from the fourth oldest university in this country. And this one is the second oldest. I want to thank the organisers of DEMA, or at least my fellow organisers who have done most of the work. To thank Rosemary and her colleagues for inviting me to spend time here. What I'm going to speak about now is the product of the time I've been here. I also had an idea that on the back burner, which I managed to pursue. I've also been pointed in other directions thanks to Heiko Grossman, mainly through incidental comments that he has made. I've got a fair amount of material, but it's all fairly simple, and I changed the title. I've introduced the term copula here, which on reflection I should have had in from the start, although it reflects the progress I've made. So there's two main contents. I'm going to explore classes of models, particularly for ranking of three products, triplets, and then explore the use of an algorithm for fitting such models. A more finer breakdown, and look at pair comparisons first of all, then triplets, the model fitting, and an algorithm for doing that. So, first of all, pair comparisons. If we have several treatments or products, and we present a pair to a subject, or the pair TI-TJ to NI-J subjects, we observe simple frequencies, those who prefer I to J, those who prefer J to I, which must add up to the total NIJ. And an expansion of that would be to ask subjects to consider three products or treatments and to order them according to preference. An example in a publication by Prendergrass and Bradley is the following. They had 4 products, 4 treatments, presented 3 of them to 40 subjects, and each triplet to 4 sets of 40 subjects. Here's the data, which we will look at later on. But models, for the pair comparisons case, clearly a general model would be binomial, OIJ being binomial with probability theta ij, and theta ij, theta ji must add up to 1. The Bradley-Terry model introduces a set of parameters, or 2 for each treatment, and theta ij is simply as this simplistic formula of theta ij is pi over pi plus pj. But this has a latent variable, or a utility interpretation. If we let lambda be the log of the p's, then our theta ij is in fact given by the logistic distribution function with an argument which is the difference in the logs of the p's. That was not the first model. Thurston used the normal distribution instead of the logistic back in the 20s. In general, what we need is some symmetric distribution to define a model. The latent or utility background, these lambda parameters are placing the treatments on a linear scale, and the difference in the lambdas are differences between the treatments. A way of generating a model or thinking about it is that there are some underlying random variables x1 to xj, expected values lambda j, constant variance. Let z be standardized differences xi minus lambda I. Ti is preferred to tj if with probability that xi is larger than xj, and that comes down to a distribution function with difference argument lambda I minus lambda j. A minor point about symmetrization, but we need a symmetric distribution. In fact, we could generate a whole class of symmetric distributions in at least two ways. Take some arbitrary univariate distribution function, then here's a combination of that one and the distribution of negative x, if x is distribution g1, negative x is distribution 1 minus g1 with negative argument u. But here's another which I kind of stumbled on, and in fact I think initially I didn't realize it was a distribution function. And we're going to explore generation of models for triplets following this particular formulation, that for some arbitrary distribution function g1, here is a possible model for the pair comparison situation, and here are two alternative expressions for it, g of u, g1 of u over the sum of these two terms, or 1 over 1 plus their ratio. Let's look at triplets, which is probability that given that treatment I, or product I, is preferred to J is preferred to K. What do we want in terms of a model? Of course, there are models in the literature, the multinomial logistic in particular. But first of all, here there are some models in the literature, three that we're going to see. The Pendergrass-Bradley model has a simplistic form that theta ijk is parameter pi squared times pj divided by d, and d just makes sure the probabilities add up to 1. And this is a fairly symmetric choice. In particular, it ensures consistency between ranking by preference and ranking by dislike, or dispreference. But if we then focused on working out the marginal probability that Ti is preferred to Tj, we don't get the Bradley-Terry formula. Plackett-Luce came up with this one, and this does ensure the Bradley-Terry formula for pairwise comparisons. Also that the probability that Ti is the first preferred is given by the first product. There is this is a product of these two probabilities here. But we don't have the symmetry in that case, but maybe that's not something we would want. Benter took the Plackett-Luce formula forward a bit and introduced parameters alpha and beta. The 3-term denominator is per alpha, the 2-term denominator is per beta. And I think these alpha beta parameters need to add up to 1. There is a scaling issue that we'll see later on. So these are three models that are in the literature, which I at the time thought were fairly simplistic, but I've now perceived in my time here that they can be generalized. So what we're going to do is end up coming up with models for theta ijk, which are of this form: some distribution function, joint distribution function uv, divided by a term d, which just ensures that the 6 probabilities, the probability of the 6 possible orderings adds up to 1. And these now depend on the successive differences lambda I minus lambda j and lambda j minus lambda k. And first of all, we focus on equivalence of this case formula for the pairwise case. This was my first thinking about this, not an expert in pair comparisons or ranking. Okay, let's think of our probability theta ijk being the probability of this ordering in 3 random variables. Well, that's equivalent to first difference here, xi minus xj being positive, and the xj minus xk being positive, and bringing in a distribution function. That probability then is some joint distribution function f2 with these two arguments, the differences in the lambdas. If we're going to base a model in this, there's various things we need, and a key one, of course, is we want the probabilities to sum to 1. Possibly negative correlation, because those two differences, xi minus xj and xj minus xk, are negatively correlated. It might be desirable to have some marginal probability that Ti is equal to Tj to be given by f1 of lambda I minus lambda j, and possibly symmetry between ranking and inverse ranking. I think taking them in reverse order, 4 is ensured by symmetry in x and y of the joint distribution function. We're looking for marginal distributions to define the pairwise probabilities and negative correlation. Well, the key thing is that we need these 6 terms to add up to 1. So that's taking this joint distribution function f2 and plugging in 6 pairs of arguments and getting we want them to sum to 1. This would be true if our xi's had normal distributions. The pairwise differences, the joint distributions between them would be bivariate normal, and all of this would be guaranteed. But of course, the bivariate normal is a bit hard to work with. So, first of all, some points about symmetrization. We could take an arbitrary joint distribution function and symmetrize it by averaging G2 with argument Z1, Z2, and then the Z2, Z1 arguments. We might want symmetry in the origin, but I'm not so sure about that. Well, here's one possible way to proceed. Copulas are simple ways of generating joint distributions, and they have now been beginning to be used in design. I've used them with a student, Nejla Gunduz, in contingent valuation studies. Copula define G2 UV to be function H with 2 arguments, and the 2 arguments are going to be marginal CDFs. HRS is a copula. It's a joint CDF on the unit square, 0 to 1, and the marginals, if you set S or R equal to 1, the H is equal to R or S, and we might want symmetry in this choice, in our choice. So HR1 is equal to R, H1S is equal to S. So this guarantees marginal distributions as well. Copula, a way of choosing joint distributions which will guarantee particular marginal distributions. Placket copula is one that's looked at. There's a formula for it. Key thing is it depends on a parameter psi. If that's lower is positive, but below 1 implies negative association, larger than 1 positive association. So here's a proposal. Possible choice for theta ijk is to take, let G2 be a copula function and define F2 UV to be G2 divided by D. And that guarantees 6 probabilities summing to 1 with, and if H is symmetric, we've got symmetry in this distribution. And it turns out marginals for this are the kind of symmetric marginal distributions that I mentioned earlier. The Plackett-Luce model, that was one model. Now moving on to a second one which generalizes the Plackett-Luce. We can break up this formula into the product of these 2 ratios, and the first term looks like it's the probability that Ti is first preferred, and then we have gone on to look at J and K, and J is probability of being second preferred. This suggests one general form that theta ijk is the probability that xi is bigger than both j and k, xj and xk, and then we've got the marginal probability that xj is greater than xk. So this first term becomes probability that 2 x differences are positive, and then there's a marginal probability for a third one. Well, following the same idea as before, this suggests that a general form of model would be that theta ijk is a joint distribution function f2 with arguments now lambda I minus lambda j, and still lambda I first minus lambda k, then we have lambda j minus lambda k in the argument of a marginal distribution. And so this formula is a product of a joint CDF and a marginal CDF, and we then pursue the basic idea. A possible choice of model in this case would be to take G UV to be G2 UV to be a copula function, but now with arguments f1u and f1u plus v, and then a marginal f1v. And then we need to divide this term d. Now, the previous one, I forgot to point out, could be, we've asked what's your best preference, and then the second, the marginal probability here could be viewed as the probability of identifying what is the worst. We could think about a variation would be worst best, and now there is the change is that U and B have swapped roles and have swapped around the roles of U plus B and B, but in fact if your F2 distribution is symmetric, that doesn't really matter. So a possible choice in this case would be G2 is copy of the function H, now with arguments F1 of U plus B and F1B, and then a marginal F1U. And we could do the same with the Benter model. G2UB to be copular, now with arguments F1U to the alpha, F1U plus V to the alpha, and then there's marginal F1V to the power beta. And then a worst best version of that as well. It's also just occurred to me in the last 24 hours that we could generalize the Pendergrass-Bradley model in a similar way, bringing in these extra parameters alpha and beta. So that's one class of models based on the first formula, first way of looking at a marginal, a pairwise probability for theta ij. Here's the other one, sorry, where we take it as 1 over 1 plus the ratio G minus U, G1 minus U over G1U. If we look at the Bradley-Terry model in particular, theta ij is 1 over 1 plus y, where y is the ratio pj over pi, and that's this G1 ratio. And G1 is the logistic distribution in that case. Well, pursuing that same idea, the Pendergrass-Bradley model could be generalized to this form, where G2UV is this expression here. Y is the ratio F1 minus U over F1U, and Z the corresponding ratio for B. F1 is a univariate CDF, and the logistic gives you the Pendergrass-Bradley model. Likewise, the packet-loose could be generalized in a similar way. And the Benter model as well. And that's 7 models we've come up with. We've mentioned marginals earlier on, but in fact, in the cases of models 1, 2, 3, 5, 6A, and 6B, the marginal distributions, if what is not clear is that these joint distributions, these formula we're coming up with for this G2UB or F2UB, it's not entirely clear to me that these are joint distribution functions. But if you allow the argument U or B to go to infinity, then you get these marginal formulae, which are certainly univariate CDF. So that's a link with that way of symmetrizing an univariate distribution. So, well, there's a summary of the models here. And as I say, there's more could be done. Symmetrizing or not, the ones that are asymmetric, and that's models 2, 3, 6A, 6B, and 7A, 7B, we could symmetrize them by calculating an average of the relevant ratios, or calculate ratios of averages. Each of them, there's a G2 value of a D value, average the G2 values, average the D values, and then calculate the ratio of those. So some ways of generating more symmetric models there. Or even if we didn't want symmetry, but a possible alternative model would be some convex combination variations of the averages involved here. So we've got a flexible class of models, parameters psi, alpha, and beta, the copulate H itself, convex weights if we followed that previous idea, a flexible class of models. And one further thing is, given a model for a triplet ranking, we can derive models for first preference, least preference, or even the middle one, if we were interested. I acknowledge that normally the P terms here would be defined by some generalized linear model structure, an exponential, say, of beta transpose xi, which would then lead also into design problems. But I'm focusing now and simply estimating the parameters P, because that brings in a link with optimal design. In all the models, these term differences U and V are logs of ratios of p-values, which are therefore invariant to proportional changes in them. Some scaling needs to be done to pin down unique values. And here is one possible constraint, but there are many, many others. What we're saying is that in the case of two, the criteria, well, the implication is that not just U and V, but our theta ijk's, our likelihood, our log likelihood, are all homogeneous functions of degree 0 in the p's, and a constraint is needed to pin us down to unique values. The likelihood in particular, our log likelihood, is constant along rays running out of the origin in this two-dimensional situation. To identify a maximum, we need to cross all of these rays in some way, and a simple choice is, in this particular case, would be P1 plus P2 equals 1. But there are many, many others we could use. So sigma pi equals 1, or sigma pi to the first c equals 1. And in fact, just thinking about that constraint, which I think leads to the argument that the alpha beta parameters in the Venter model need to be scaled in some way as well. So a constraint is needed, and I'm focusing on the p's adding up to 1. And that means they're like optimal weights, or weights, and we know how to find these in optimal design. And we have an example of this problem. Optimality conditions are simply that the first partial derivatives are 0. As it happens, they are like, in this particular case, the partial derivatives are exactly the same as what we would call directional derivatives in this particular case, because the sum pi di is equal to 0 for the homogeneous functions of degree 0. So all our p's must be positive. It's a simpler situation than in the design problem. Algorithm, choose a function here of two arguments, d and delta. D is derivative, delta is a free parameter. If d0 should be a constant, the function should increase in d. Some choices here. Algorithm, multiplicative algorithm, ensures the constraints of positivity in summing to 1. You take current iterates, multiply them with this function f, evaluated at gjr, partial derivatives at that iterate, for some choice of this parameter delta, and then scale so that they sum to 1. Properties, it's always feasible, this iterate. The directional derivative at pr towards pr plus 1 is greater than equal to 0. And equality, but you would have equality when all the GGs are equal, corresponding to positive values at a local maximum or optimum. If delta is 0, there's no change. So the algorithm should be monotonic for small positive value of delta. If you let delta be too large, it won't be. So that's the key properties. Here's the proof of the result that we have a positive directional derivative from PR to PR plus 1. Choice for our iterations, take F to be the standard normal CDF. So there's the iterations. Suitable choice of delta. Well, first of all, it makes sense to scale our observed frequencies to relative frequencies. So divide by, first of all, determine 1 over n, and the total count. So this is here's an error here. This would be appropriate for the marginal, the pairwise case. But n is the total number of counts, so the sum of all the counts we've got. And then we want to take that and multiply it by some alpha value between 0 and 1 is likely to be a sensible choice. Starting with the initial iterations, uniform iterations, I've explored this, fitting the full triplet model in the range of situations to the bivariate and the best worst, for the Plackett copula, normal marginal distributions being normal and logistic, 10 values of psi. Then to the full triplet ranking for the worst best scenario, just for 2 values of psi. first preference, two values of psi. You get convergence fairly quickly. I'll get comments about that later, but I keep it going until we get derivative, first order derivatives to 0 to 6 decimal places. There was one exception to all of this. By the way, I took alpha equal to a half in these cases, and that was purely incidental. I'd forgotten I'd changed that in the program that I amended, but I just stuck with it. It was working. But it didn't work in one case, and in this particular case, psi equals 0.1. I had to divide by 10 to get convergence. I again looked at the original Prendergast-Bradley and Plackett-Lewis models, and it's a similar story. So the algorithm seems to work fairly well. It certainly it works very quickly initially, as others have found, but then it is a bit slow, but it gets there usually in the end. Well, I'll leave it there. There is other problems. A key one is to extend to more than triplets, and some work has been done in that already, but the models that I spoke about here could be generalized for rankings of more than 3 products. For example, so this. I'll leave it there.
Okay, questions for Ben?
Hi Ben, I don't fully understand your use of copulars, but there are of course multidimensional copulars.
Yeah.
I wondered if you could, knowing that there's a whole theory of multidimensional copulars out there, I wondered if you could use those to lift your U's and V's to a multivariate setting.
Well, that certainly would be appropriate here.
That's what you're doing there.
Yeah. But the reason for the copula was just they were simple ways of guaranteeing, say, particular marginal distributions, and they were explicit as well. Whereas for the bivariate normal, if you want to evaluate the bivariate CDF, you need to use numerical techniques. There's no explicit formula for it.
As far as I understood, your criteria is not convex.
Possibly, I haven't checked. Yeah. It's a likelihood.
Yeah. And therefore, your conditions are only necessary conditions.
Yes,
How do you know if your algorithms don't converge to some strange local minima or some saddle points or anything like that?
Oh, I haven't checked that out. Yeah, but that clearly is an issue. Yeah.
But did you have cases when you have more than one local minima or
Well, no, I've never. I would need to do exploration of that. I've only ever chosen the starting point as the uniform. I think to do what you're saying, we'd need to consider a range of starting points. By the way, one other point would be that, say for that parameter psi, if you found the optimal values for a given parameter value of the parameter psi in the copula, then, and you want to work out for a value of psi not far away, then presumably you've got a good starting point.
Any other questions? Okay, so let's thank Ben and all our speakers again.